Um, okay, good afternoon, everybody. Today we will go to new model architecture sequence to sequence. But before that, I want to, and the translation, but before that, I want to finish our previous homework because we had not very good suggestion from ChatGPT and I want to fix that first and also show how to add GPU if you want to run it on GPU, even though homework 3 doesn't. Well, you can run homework 3 and homework 4 without GPU, but maybe it will speed up. Or you said. Uh, okay, so let's finish our previous assignment. And by the way, because in homework 3 you just need to write the perplexity for function and another model where you change convolution to, for example, LSTM. I don't want to extend the deadline because we have new topic which will require much more work from you, the attention. It will require attention. I mean, not your attention, but the mechanism of attention. And of course, it will require also your attention. And but if you need extension, just write me email. But I don't think you just need to change 2 cells actually for homework 3. Okay, so let's open this in Colab. Fold. So last time we stopped on this loss function, and I want to use a little bit nicer formula also, which will use built-in cross entropy, but without this U and shape. So it, where is it? Aha, as follows. I believe it's a little bit easier to read. So here we just because cross entropy uses the last channel as the dimension, so we change the channels of our output probabilities. And yeah, I think it's a little bit easier to read than this line. So now I will also show, and you can watch later the video recording, where to add the GPU device. So the first, okay, and also I will comment our another implementation of this loss function. And also I will comment print. So the first place in where we add, so how to add actually a GPU device? So you can assign the create a variable device, and in the most cases it's called CUDA, but in Mac notebooks it has another name. I don't remember. MPU. Yes. So if you want to use your MacBook GPU, then use this name. So I will use this suggestion. CUDA if it's available. Otherwise we will use our CPU. And the first place where we move our tensors. Oh, wait a second. I should actually run everything, maybe. Mhm. Okay, first I will send my tensors and models into device, and then I will run everything. So the first place was in our class in function get possible tokens. So if I want to apply model on GPU, where is it? Somewhere we should apply our model. Then the input should be also on GPU. Okay, I believe the output of this model is used in another function. So I will add here device um, device equals device. Then there are just 4 places where we should add this. The second place in compute loss, because when we compute loss, we also use the model here. So, and because model will be on GPU, the input should be also on GPU. Mhm. So the third place in the assertion, we use dummy model. So we should pass this model to device. Dummy model to device. And the last place here, hint if you want to use GPU. So here we should pass our model to device. Okay, now I will just switch to GPU mode. Mhm. And you can connect GPU. Oh, because I reached, okay. So I can't run this on Collab. So when I will run my code, it will run on CPU because there is, okay, I should switch. Because my device was defined as GPU if it's available. Okay, so this was from our last time. And I just want to see that everything works. Something didn't work. Now the tensor. see. Okay, yeah, so and we created the model. And we created model with convolution layer. Let's see. Right, slow, so slow. So if you run on CPU, you don't need to wait until you go through entire epoch. You can stop when you will see that your loss dropped, and then you will pass assertions. Okay, so now let's go to our new. Yeah, I used a lot of GPU 2 days ago, so that's why I don't have ours today, but I believe they will restore it next week. So, yeah. Yep, where was it? So for loss function, we have input. Input is the batch of sentences and transformed into integers. Then we apply our model to calculate the probabilities of the next token. And we take all except the last one, and the reference will be kind of next token, so shifted by one. And finally, we calculate the mask. The mask will take values one for the sentence and the first end of sentence token, and zeros for the padding. And finally, so there is another way to write this loss function. Last time we talked about this, but nicer way is to use the built-in function, which we apply to logits and the targets, and reduction none, so we don't average it. Then we apply mask to our loss function, so we will zero the logits with corresponding to padding. And after that, we will sum up and normalize, and we will get this because we use percentage, or another way was to use log softmax. We will get the sum of logarithms of probabilities for all tokens except paddings. Okay, so let's go to our today's topic. And one more thing about also from last class. You remember we talked about perplexity, and we defined the perplexity per token. So we divided this by the length of our sentence. So what do you think? So we looked at two models. One model was using tokens, the words. The other model was operating with characters on the character level. So what do you think if we calculate perplexity for model which uses words, and perplexity for the model which was trained on characters, can we actually compare the perplexities of these two models? So for example, if one perplexity is high, can we say that that model is better? So I kind of want to to clean up all the previous stuff. So I forgot to mention this. So what do you think? Can we compare two models by perplexity if they were trained on one on the tokens, on the words, another on, well, characters are also tokens on characters. Yeah.
I want to say no because it's trained differently.
Because it's you remember we use perplexity per token.
Right.
And then in one case we will have words, in another case we will have characters. So we just can't compare this with this. So we can compare models by perplexity if they trained on the same tokens. Okay, I just want to mention this. Okay, now we're going to go to the new topic. So do you know what does it mean sequence to sequence model? Well, yeah. For example, if you work with time series predictions, if you want to predict the value on one step ahead, then you can use any model. But if you want to predict on several steps ahead, then you create one model, for example, one recurrent neural network, and the other recurrent neural network, which actually the second neural network will have the size of the steps, how many steps you want to forecast forwards. So this is, I don't know, if you maybe you worked with time series, then you would be familiar with this Seq2Seq model. But we will use this model for translation. So for example, if we want to translate from one language to another, we want to predict multiple tokens, like a new sentence. So let's talk about this problem. You remember our language model predicted next token. In case of translation, we will use condition models, and they will be conditioned on the input sentence. So our model will generate a new token, but it also will generate this new token based on the input sentence on the other language. And that's why here we see this conditional model. X is the sentence on one language, and Y is the sentence that we want to generate on the other language. And because we will use neural networks have parameters, some weights. Okay, so let's look at the model and how to train this model. So a sequence to sequence model uses this idea of encoder-decoder model. In encoder, we will read the sentence on one language, and you can think about this as one recurrent neural network. And in decoder, we will generate tokens, but on the target language. And this will be another neural network. And here is how we will get the probability. So now the decoder will generate, for example, what will be the first token that will generate our decoder?
I, like the first word, or
Begin of sentence.
Yeah, beginning of sentence.
Yes, the token begin of so for example, we have begin of sentence and we have the input phrase on one language, and we want to generate a new token. So we will calculate these probabilities, and finally, when we will stop, when actually we will stop generating tokens.
End of sentence.
Yes, when one of the tokens that we choose will be end of sentence. So, and then we take the product of all these probabilities. And again, it's a likelihood idea, and we will maximize likelihood. And here's the visualization. First, we create embeddings for dictionary. So you remember this processing, create embeddings. Then we pass these embeddings into the encoder, and for example, take the last output from LSTM and use this last output as the state input to the new LSTM. And the first input will be begin of sentence. And then our second model will generate new hidden state, and this hidden state will be transformed into the size of the dictionary, and then we will choose the new token with the highest probability in this dictionary. So this is the general idea of this model. Yeah, so when we have the new hidden vector, we apply linear layer to transform this to the size of the dictionary, and then we and then so it works differently in training and actually inference. So in training, we have the exact pair, the translation. In inference, we don't have the translation. In inference, we just have the input, and that's it. So now it's this slide represents training. When our hidden vector is transformed to the size of dictionary, we actually know what should be the next word during training. And so we can maximize this probability based on the known class of the next token. So let's see. I believe, I'm not sure if it's training or inference. So begin of sentence and the output from the first recurrent neural network results, for example, in I. Then this output will be the state input to our recurrent cell, and the next token will be actually this I. Then it will generate next hidden vector, and the maximum probability will correspond, for example, to the token sol. So we will use this token as input, and so on. So this is how it works on inference. And we stop when we reach end of sentence. Okay, so it's interesting that if we visualize using dimensionality reduction into dimensional space, the embeddings of this last hidden vector from the encoder, they will group together not by the words, but by the meaning. So, for example, here, Mary admires John. John admires Mary. They have exactly the same words, but these phrases are grouped not by just the word counts, but by the. So it's interesting observation that the last hidden vector from encoder actually captures not only the words, but also the meaning of phrases. Okay, this was modeling. How to train model, I also explained that during training, we know the next token. And we force our model to get higher probability for this token. So this is how it's trained. And finally, how we choose the next token. As you remember, we talked about these different techniques. One is called greedy strategy, when we take the next token with the highest probability. So the maximum of the product is not the same as the product of maximum of individual components. You remember, there are two other techniques. Nuclear sampling, when we choose words based on the joint probability, and top case sampling. There is also beam search. So beam search works as follows. I believe this is beam search of size 2. So you have the first token, and then you have the distribution over all tokens, and you choose for, in case of just two tokens with highest probability. Then for each token, next token, again, you have the distribution of the next token, and you choose only if the beam size equals 2, you choose just two tokens with highest probability. And for the second token. But then you keep only 2 from these 4. So it will reduce the complexity, otherwise it would be the size of dictionary power number of tokens, so it's astronomic number. So this idea is called beam search. But in practice, we typically use just the top case sampling. Okay, I think now we can go to the code example. And next time we will add attention into our model. And in your homework, so I will code with your attention, and in your homework, I ask you to implement 2 different attention mechanisms, because there are many variations. Okay, where is the code? And I believe this is one of the most complicated topics in this entire course. Okay. So we will translate from French to English. Here it's from English to French illustration. And Oh, and let's download the data set from Kaggle. From Kaggle. And it's nice they made this API that you can download directly from Kaggle. Then we will need the file vocab, and vocab. So instead of writing from scratch again tokenizer, vocab actually will take care of this tokenization. Also, I will. What's that? Let's see. Oh, I should use exclamation sign. Unzip. Um, yeah, I think we don't need this import CSV. And now the code for tokenization is written for you. Oh no, we need this CSV. And what we will use here is called BPE, byte per encoding. So what is this byte pair encoding? Let's say we have the dictionary with 3 words, ABA, CBA, and AAA. So byte pair will encoding will look for most frequent pairs of the characters. So in this case, AB will be the most frequent pair. So it will combine the pair AB into one token. And we will get, now AB will be just kind of one character. And this word will contain only 2 characters. And the next will be C A B A, and the last one will be AAA. So in the original data, we had also word pair BA. But after this encoding, we don't have BA at all. So our the number of pairs is now smaller than in the original data. Then our byte pair encoding will provide the same procedure, but on this new data. So now we have token ABA, ABA, and AA. Well, if we have 2 pairs with the same frequencies, it will choose, I don't know how, maybe randomly one. So if we choose ABA, then it will collate them together and create a new token ABA. And then the first word will be just one token. The next will be CABA and then AA. So this is how this tokenizer works. And if you look at the result, so here you can indicate the maximum number of tokens. So in this case, I'm using 8,000. It means that we will glue these subwords together, and when our dictionary reaches this size of 8,000, we will stop. And here is the phrase. I don't know why this phrase is very popular in NLP. A quick brown fox jumps over a lazy dog. And this is the result of tokenization. You can guess that quick became one token, brown also became one token, but there is no token jumps. And it makes sense because it's the modification of jump. It's split into two subwords. If we use what do you think? If we use smaller size of dictionary, will we get more splits, or we will get more whole words? If I use, for example, 4,000, so it takes some time to iterate through the entire data.
More splits.
Yes, yeah, because we will have smaller dictionary. Yeah, now Fox also was. Um, okay, so this is and actually in all large language models, this tokenizer is used because in this case we kind of have the balance between the size of the dictionary. We don't use all the words, but also we are not limited by individual characters, because if you would like to run character-wise model, if you remember how ChatGPT works, it just prints new token at a time. If it would use characters, you would need to wait much longer. So it's kind of the trade-off between the size of the dictionary and the computational complexity. Okay, so it was just the pre-processing. Here we create this byte pair encodings for two data sets, for data set with English phrases and French. So the data set looks as follows. Let's see. It actually, David, who was here, he actually used this data set for his projects in machine learning class. So it's just the pairs of sentences in English and French. And from these sentences, we create separate data sets, only with English, only with French, and apply tokenizer. Okay, so, and here's the result of our data set after tokenization. The word in French, the word in English. What do you think if I would apply French tokenization to English text? So let's try to apply um, where is it? For example, the English dictionary to the French sentence. What do you think we will get? Okay, but I will change this to English. I don't know French. AI assistant knows knows it better. And okay, because it doesn't know these tokens, so it just use small. Also, every individual character will be in your dictionary after BP tokenizer. So in the worst case, you would get just character-wise split. But in on the other hand, you never have unknowns. You remember um, when we used account-based encoding, we had unknowns for tokens outside of our dictionary. In this case, we don't have unknowns at least. Hmm. Okay, so finally we convert our sentences into numbers. And these are just very short sentences of one word. So that's why we have this matrix begin of sentence index has index 0. Then this index corresponds to this token. Then this 19 will correspond to the period. And 1, what do you think? Um, which token corresponds to 1? Yes. We could introduce also padding, but we use end of sequences padding as well. We will just take care of the position. So if it's the first of end of sentence, then the rest we will just use mask with zeros. Okay. Here's just distribution of the tokens between in different languages. And here is our model. We have just 2 minutes left, but it's very straightforward. We create embeddings for English and French dictionaries. So this is the size of the dictionary, and it maps to this shape of embedding. We use recurrent neural network. GRU is in between RNN and LSTM. It doesn't have the cell state, but it has hidden state. And here is our model. Encode. In encode, we apply a recurrent neural network to our input batch, and we get the encoded sequence, and then we apply linear layer. Let's see, somewhere we should apply linear layer. Maybe we will apply it later. So, and we take the last output from RNN. Then in the code step, we use this last output from our first RNN as our input to second recurrent neural network. And then we use the begin of sentence token, but we will use instead of LSTM, GRU will use just GRU cell. And you maybe remember, if we do a for loop over GRU cell, it's the same as applying the entire layer. But I think we should stop now, and I just will show the results. So if you apply this simple model, then you will get some reasonable translation. Like this is the input text in French, friend plus, and it's not a very good translation. But when we will use attention, then actually we will get pretty accurate translation. And this model was with attention was used up to last year. I don't know what about this year. Maybe large language models are used now, but it was used in all Google translators up to last year. Okay, so that's it for today, and we will go into details next time then. Just because it's really important to understand this model and introduce attention to understand transformers later and to do the homework.